Hello everyone, I'm Markus Frey and I'm very happy to present my work Probing Neural Representations of Scene Perception in a hippocampally dependent task using ANNs. In this project, we examined the neural circuit diagram that connects the visual cortex to the hippocampal formation, aiming to develop a task that necessitates processing throughout the entire neural hierarchy. For instance, a basic odd-one-out task, such as the one displayed in the lower right, only requires color discrimination. A more intricate odd-one-out task, as the one in the middle, has been shown to demand a fully functioning perirhinal cortex. Our goal was to identify a task that involved the hippocampal formation as well. We ultimately found this in the previously described for mountains task. Inspired by this task, we introduced the allocentric scene perception benchmark to test neural networks on their allocentric scene understanding as well as object segmentation performance. Additionally, we developed a neural network model following biologic connectivity as close as possible. We use this model to perform unsupervised object segmentation, which allows us to obtain state-of-the-art results in Cater and a subset of movie benchmarks. The Four Mountains test works in the following way. Participants or patients are first presented with an image featuring 4 mountains. After a 2-second delay, they are shown 4 distractor images. 3 of these images display different scenes, while one image depicts the same scene but from an alternative viewpoint. If you want to guess for yourself, pause the video now. In this case, the correct response would be the upper right image, depicting the same scene slightly rotated clockwise. This task has been previously shown to require a fully functional hippocampus and is used in clinics to predict Alzheimer's disease conversion with high accuracy. We deconstructed the task into its fundamental components, utilizing a global reference frame and rendering 4 objects using cones. Additionally, we generated segmentation masks and depth profiles for each scene. We call our new scene the allocentric scene perception benchmark, which, in contrast to the original Four Mountains test, can be used to train neural networks. We next constructed a model inspired by biological connectivity to simulate the neural hierarchy from the visual cortex to the hippocampal formation. We used a pre-trained CORNET model to emulate visual cortex with connections to higher-level cortical areas, such as the parahippocampus, perirhinal, medioentorhinal, and lateroentorhinal cortex. This model was trained using a triplet loss connected to hippocampal area CA1. During the training process, we sampled an anchor and a positive image, both from the same scene, but with different viewpoints, and a negative scene where the object's locations were altered. To evaluate the model's performance, we sampled thousands of triplets and computed the mean off-diagonal across model representations. In each triplet, the sample with the highest correlation was taken as the same scene sample, which allowed us to calculate an accuracy score across layers. As shown on the right, the pre-trained layers performed at chance levels, indicating their inability to distinguish between the same scene from varying viewpoints. In contrast, higher cortical areas demonstrated significantly better performance, with CA3 and CA1 correctly classifying around 90% of the scenes. After training the model to differentiate between scenes across viewpoints, we can visualize model representations across different reference frames. Here, schematically shown for 2 images of the same scene but different viewpoints. In the egocentric reference frame, the highlighted mountain changes its screen coordinates from the top image to the bottom image. In contrast to this, the allocentric schema shows a world-centered environment in which the highlighted mountain has by definition the same allocentric coordinates. We also sample snapshots from within the scene for visualizing spatial responses from an agent perspective. When we plot responses with respect to these reference frames, we see spatial responses reminiscent of the ones we find in freely moving rodents. These include place cells, which have classically been described as encoding one specific place within an environment, head direction cells, which encode the head direction, as well as grid cells, which show periodic firing pattern as a response to non-periodic behaviors. We also detect remapping across scenes, indicating that the same neuron has a different preferred spatial location when visualized across different scenes. We can now use the same model on scene segmentation benchmarks, like the ones shown here. These benchmarks assess the model's ability to segment all objects within a scene into distinct classes. For this, we adapt our model with a feedback loop, which takes information from CA1, splits it into temporal and spatial pathway, is then concatenated with CA3 and is fed through a pixel-wise decoder to reconstruct the image and provide unsupervised segmentation masks. We demonstrate that this architecture, along with feedback connections to visual cortex, enables us to achieve state-of-the-art segmentation performance on cater and movie benchmarks. In summary, we present an allocentric scene perception benchmark and a biologically plausible neural network model, capable of distinguishing between hundreds of scenes. This enables us to reconstruct images from null viewpoints and perform unsupervised segmentation.